Welcome to section 7.1, which is systems of linear equations. We're going to learn in general just about systems of linear equations and what they are. We're going to talk about how to identify whether you have a solution to a system of linear equations, and we're also going to learn how to solve a system of linear equations with the graphing technique. When you have two or more linear equations and you're trying to solve them all at the same time, that is considered a system of linear equations. In this class, we're going to stick to just two equations at a time, but you can have 3, 4, 5, 6 equations. The solution to the system of linear equations is going to be an ordered pair. Specifically, it's the ordered pair where the two lines cross if you were to graph them. So when you get your answer, you need to make sure that you have both an x and a y value written as an ordered pair as your solution. Systems of linear equations can have one solution. Sometimes they'll have no solutions at all, or you will get a unique situation where you have infinite solutions. The first thing you're going to encounter on your homework is deciding whether or not an ordered pair is a solution to the system or not. The easiest way to do this is to substitute the ordered pair into the system. Okay, so let's look at our first problem. Our two equations are 2x minus y equals 6 and 2x plus y equals 14. Let's check and see whether 0, negative 6 is a solution. To do this, you're going to place 0 in for the x and negative 6 in for the y in both equations. And you want to verify if it makes true statements or false statements. So if you look at the first example, 2 times 0 is 0. 0 minus negative 6 is the same thing as 0 plus 6. So you do have a true statement for the first equation. 6 does equal 6. So let's verify the second equation. In the second equation, you have 2 times 0, which is 0, and plus negative 6 is the same thing as minus 6. 0 minus 6 is negative 6. And that's bad. That's a false statement. So because the ordered pair did not work for both of the equations, 0, negative 6 is not a solution. So let's try our next ordered pair. Let's try the 5, 4. So we'll do 2 times 5 minus 4 equals 6. And 2 times 5 plus 4 equals 14. 2 times 5 is 10, and 10 minus 4 is 6. So it works for the first equation. 2 times 5 is 10, and 10 plus 4 is 14. So it works for the second equation. So because 5, 4 worked for both equations, this is a solution to the system. Now remember, there can be infinite solutions, so we still should check our third ordered pair to see if 3, 8 will also work. So let's try it. 2 times 3 minus 8, and 2 times 3 plus 8. Let's see what we get. 2 times 3 is 6, and 6 minus 8 is negative 2. Negative 2 does not equal the 6, so it is not a solution. You can stop right there. If you want to check the other one, you can, but honestly, it doesn't matter if it works or not. To be a solution, it has to work for both equations, so as soon as it failed the first equation, you could have said it was not a solution to the system. Usually they won't tell you the ordered pair where they cross. Usually it's up to you to find the ordered pair where they cross. So the first method we're going to use to do this is the graphing technique. In order to do this, we are going to graph both lines. One way you could do that is you could find 3 ordered pairs on the equation. You could plot the ordered pairs, and then you could sketch the lines between them. Where the two lines cross each other is going to be considered the solution. There's going to be 3 different possibilities that you can encounter. You can find 2 lines that just cross each other at one point. If that's the case, they're going to call this system a consistent system because it has a solution. An example of what that would look like would be this picture. You have your red line going uphill, your blue line going downhill. Your solution is your point of intersection located at 1, 3. So again, the solution is 1, 3, and this is consistent. You can also run into a situation where the lines do not cross each other at all. If the lines do not cross each other at all, there's no solution, and this would be considered an inconsistent system. When you go to graph the equations, they're going to look like two parallel lines that never touch. So if they don't touch, there is no solution. If there's no solution, the system is called inconsistent. The last thing that can happen is you can have an infinite number of solutions. This is going to happen when they've given you the same line twice. This is called a dependent system. When you go to graph it, it's going to look like just one line on your graph, and that's because the two equations were the exact two same equations. So technically, there's infinite solutions. Any point that lands on the line is going to be considered a solution. So if they ask you what your solutions are any point that's on the line y equals negative 2x plus 3. There are infinite solutions since lines go on and on forever. When you run into that situation where the lines are on top of each other, that is called a dependent system. Okay, so let's try and solve one on our own. Let's say that we are given the equation x plus y equals 4 and 2x minus y equals negative 1. There's lots of different ways that you can graph it. Let's graph the top one first. X plus y equals 4. An easy way to graph that is to find your x-intercept. If you're trying to find your x-intercept, you just set y equal to 0 and solve for x. Your x-intercept is located at 4. Then you can find your y-intercept. To find your y-intercept, you would set x equal to 0, and your y-intercept is also located at 4. And then you can connect the dots if you want to. You should draw a nice smooth line between the points. Okay, now let's try to graph the line 2x minus y equals negative 1. Let's put that in slope-intercept form, which is y equals mx plus b. So to do that, I'm going to subtract the 2x to the other side. And then my y is still not alone because it's got the negative in front. So I'm going to divide everything by negative 1. And that'll give me the equation y equals 2x plus 1. So that means I should start my graph at positive 1 on the y-axis, and I should use my slope of up to right 1 to get more dots. The location where the two lines are crossing is your solution. These two lines are crossing at 1, 3. You always give the x value first and the y value second. Because there was a solution, this is a consistent system. Let's try another one. You have the equation x plus y equals 3 and 2x plus 2y equals negative 4. Let's graph x plus y equals 3 first. I'm going to use the x-intercept method again. If I'm looking for my x-intercept, I simply zero out my y, and my x-intercept turns out to be 3. So I'm going to plot that on my x-axis. If I'm looking for my y-intercept, I simply zero out my x. My y-intercept is also 3, and I'm going to plot that on my y-axis. And I like to continue the line a little bit so that you can see where they cross really well. Oops, pretend I went through all the dots. Okay, now let's graph the other one. 2x plus 2y equals negative 4. Again, you can do this really easy by finding the intercepts. So I'm going to do my x-intercept first, so I'm going to zero out my y. And I have the little equation 2x equals negative 4. So my x-intercept is negative 2. And then I'm going to find my y-intercept. 2x plus 2y equals negative 4. So I'm going to zero out my x, solve for my y, and my y-intercept is also negative 2. Oops, I put that in the wrong spot because the numbering gets a little off down there. Count the lines, not the numbers. Draw my line through the dots again. Notice that the two lines are parallel to each other and they never cross. That means this problem has no solution. and that this is an inconsistent system. Okay, last one. Let's solve the system. Y equals 2x plus 3, negative 2x plus 3. This is already in y equals mx plus b form. So to graph that, I would start at the y-intercept of 3, and then I would use my slope of negative 2. So down 2, right 1, down 2, right 1. And you can continue that pattern as long as you want. If you're doing this at home, I would recommend you get some graph paper. You can always download graph paper on the internet for free and just print it out. That's up to you if you want to do that or not. Okay, now we got to graph the other one. Okay, so you can graph it any way you want. You can graph it by solving for y. It'd be really easy to solve for y by just dividing everything by 2. When you do that, notice what happens. Y equals negative 2x plus 3. It's the exact same line. So if I went through and tried to graph it, I would get the identical line. So if you get the identical line, that means there's infinite solutions. All the solutions occur on the line, and that means this is a dependent system. As much as you don't want to do it, they're also going to throw you some story problems your way, and the story problems will get more and more complex as you work your way through the homework and through the problems. So this one has a little bit of everything in there, so let's check it out. At a collectibles show, Richard Lane can sell model trains for $35. The costs for making the trains are a fixed cost of $200 and a production cost of $15 apiece. A, write an equation that represents Richard's revenue. Okay, so his revenue is going to be his total money brought in. Okay, and we're going to call revenue R. So Richard sells the trains for $35 apiece. So if he just sold one train, he'd only make $35. If he sold 2, he'd make 35 times 2, $70, and so on. So his revenue is going to be 35 times x, where x is the number of trains that he sold. Part B. How many model trains must Richard sell? Oh, sorry, I didn't do the second part of the first question. We have Richard's revenue. The second part asked us to write an equation for Richard's cost. Okay, well, Richard has a fixed cost of $200, so that's kind of like his rent. He pays $200 a month no matter what. It doesn't matter how many trains he makes, so it's not going to be increased by variables. It also costs him $15 to make the trains, so it's $15 times however many trains he's going to make, so that's his cost equation. Now, part B wants to know what his break-even point is. The break-even point is going to happen when the revenue equals the cost. Okay, the easiest way to see that is to do this problem graphically. Okay, so I'm going to get myself a little more space. I'm going to scooch this, won't let me. Okay, I'm just going to draw a graph down here then. Okay, so X is my number of trains. And up here, I'm going to have the amount of money that I'm going to make, whether it's revenue or cost, okay? So this is money on my y-axis. Okay, and I'm going to try and figure out where these two lines cross each other. Okay, so his revenue, he makes $35 per item. He's probably not going to make just one item. So let's maybe count by twos. 2, 4, 6, 8, 10, 12, 14, that's probably far enough. Okay, so let's get ourselves a couple revenue values. Okay, so let's say that he did go ahead and make 14 trains. We can just use our calculator and take 14 times 35, and you'll know what his revenue is for that. That would be $490. Okay, so we need to count pretty high. Let's maybe count by hundreds on the y-axis. 100, 200, 300, 400, 500. Okay, so at 14, he's at almost 500. Let's do like 10. if he made 10 trains, that would be 35 times 10. That'd be 350 trains, or $350. So that's going to be right around here. Obviously, if he made no trains at all, that'd be 35 times 0. And so this is his revenue graph. Okay, now we need to do the same thing for the cost. The cost should be a little bit easier because you know the y-intercept. You know if he sold no trains at all or made no trains at all, he would still have to pay his fixed cost of $200. But if you want, you could do a little table as well. And we could pick the same points if we wanted. So let's just say if he made 14 trains, how much would that cost? So we would have to do 200 plus 15 times 14. It would have cost him $410 for 14. It's a little less than the revenue. And let's do the 10 again. Let's say he made 10 trains. You'd have to do 200 plus 15 times 10. Oh, that would be 350, which is going to be right there. Let's connect our dots for our cost equation. So your solution or your break-even point is their point of intersection. So if he makes 10 trains exactly or sells 10 trains exactly, then he will break even, meaning his revenue and his cost are going to be exactly the same. Okay, Part C asks for some more details. Part C says to use the formula to determine Richard's profit if he sells 15 model trains. Okay, so we can do that really quick. I'm going to go to a blank slide for you. So what you need to know is that profit is equal to the revenue minus the cost. Well, we know that the revenue is 35x, and we know that the cost is 200 plus 15x. I'm using parentheses there because you're going to have to distribute that negative, okay? But the question asked from Part C, the question said, write an equation for the profit formula. We do. Use the formula to determine Richard's profit if he sells 15 trains. So all you have to do is plug 15 in for all of the x's and simplify. Okay, so first we'll take 35 times 15, which is 525. And 15 times 15, which is 225. You need to do what's in the parentheses first according to order of operations. 200 plus 225 is 425. And then you can take 525 minus 425. If he sells exactly 15 trains, he will make $100. There was one more part to that question, Part D. Part D asked how many model trains Richard has to sell to profit $600. Okay, so to do that problem, we can use the equation that we wrote in the previous problem. Okay, our profit equals our revenue minus our cost. Okay, now in this problem, they told us that our profit needs to be $600. So we are going to need to solve for x in this problem. If it was me, the first thing I would do is clear my parentheses. And the way I'm going to do that is by distributing my negative. So I'll have negative 200 minus 15x. And then I would combine my like terms of my 35x minus my 15x, which is going to be 20x. Clear the minus 200 with a plus 200. And then divide each side by 20. So he is going to need to sell 40 trains in order to make a profit of $600.